our in-cab academy on our Advanced Cable Engineering System, or ACES. And as I was talking a moment ago, this system is intended to be a tool to help engineers work with area fiber optic cables, specifically OPGW and ADSS. And because it's specific to in-cab and our products, I didn't feel it met the RCEP guidelines for professional development hours. So I did not certify this course as a PDH credit course. I hope you still find it interesting and useful, but I'm sorry I can't give you a PDH credit for it. So let me set the stage. Why did in-cab develop ACES? And really the reason is twofold. Excuse me, I'm not very adept yet at how I share my screen, but I will figure it out. Go to here. And let me go to here. And again, I apologize for my awkwardness in doing this. Most of you know, and it's been practiced like forever, that when you need a cable, you would go to a catalog, you'd open the catalog, and you'd look at some kind of a table. And this is a table of cable data from where I used to work, Brood Cables. This is what's posted on the Powerline Systems cable library. And by the way, you can find information on in-cab cables there too, but I use this one because the table, it's kind of a very common format that manufacturers have used for years and years. So let's say that you were doing an OPGW project and you knew that you needed 48 fibers and you knew that required fault current of say 80 Ka squared seconds. Well, you come to a table like this and you would scroll down and look, okay, 48 fibers, that's the first thing I'm looking for. And the fault current is over here. And let's see, I need 80. And let's see, here's one. Cable diameter 0.541. I got my 48 fibers checked. I got my 80 K squared seconds. 541. Okay, maybe that's okay. Maybe it's not. Because maybe I'm already using hardware that's good for 0.585. Well, okay, here's a 587. Okay, that would probably work with the hardware I'm already using. But let's see, I got 80, I got 80 again, got different strengths. So do I need 27,880 pounds? Or here's one, a little bit better fault current, but the strength is 26,456. Here's another one. Wow, got even better fault, but the strength has gone down again. Kind of no surprise. In order to get the fault current up, you've increased the aluminum content, which means the strength goes down. But the point is, what is really optimal here? How do I know what strength? And as strength goes up, weight tends to go up with it. So I'm really effectively saying that I'm changing the strength to weight ratio. So what should I really use? So that was one thing this was intended to help. It was basically, let's stop this ancient practice of looking at data tables, which actually are not complete. They're not giving you all the information that you need to make the optimal decision for your system. Let's bring it into the year 2020 and come up with a system that walks you through a series of steps and helps pick the optimal cable for you. And the second thing that ACES was intended to do is, of course, we're still relatively the new kid on the block, and a lot of customers can't come to us and say, well, I'm using this, just give me something like this. Usually based on one of our competitors' designs. So we thought with ACES, we would give people an easy way to start with a clean slate and pick a cable that's optimal for what they're trying to do. You do have the ability, like I just outlined here, to pick a cable by diameter if you need to keep it within a certain diameter range. But you can also start with a clean slate if you want to and pick something that you know is optimal. So let me change back to ACES in one moment. All right. Yay. So the ACES system, you just go to our website, incabamerica.com. Well, in fact, we'll just do that. So america.com, website comes up. Little blurb about the latest thing going on with us, and then pick ACES. We have a quick and easy registration. Basically, we just ask you to give us an email address, and then you're free to use the system. You have different options here. You can just look at cable selection if you want to. So ACES OPG cable selection only, or ACES ADS cable selection only. Or you can look at the complete system. So what I'm going to do today is first I'm going to do an OPGW complete system, and then I'm going to do ADSS cable selection only. Because once you get past the cable selection, the steps are pretty much the same for both types of cable. It's going to walk you through to help you look at your sags and tensions, and it's going to walk you through your accessories. And also help with rear links. We'll see everything that it does, but what I'm telling you is that once you get past the cable selection, the following steps are pretty similar between the two programs, so I only need to show you that once. So let's start ACES OPGW complete system. So step one for OPGW, and by the way, it's to select your fiber count, and I don't want to miss talking about the hints that are there. There's information built into the hints, what's what. So the fiber counts is basically common fiber counts. We need to work, and we're constantly working on this program and improving it. And the next obvious step is to go up to beyond 144 fibers. But right now, it just goes up to 144, which is still pretty good. It's giving you information about fault current and how you calculate that. So those of you that have heard my OPGW Engineering 101 webinar will know that I go into that in nauseating detail. And here you get kind of a Reader's Digest summary of it, and you'll understand the basic concepts. And of course, at any time, if you have questions about something, you'll find contact information. You can reach out to us, and we're glad to help. Discussion of maximum rated design tension. Again, in my OPGW 101 webinar, I talk about that. That term comes from the IEEE 1138 standard, and basically that is the tension that you should not exceed on your OPGW under any wind or ice loading conditions. So you get some good hints here. Now, if you go down, you can begin the real process. So we'll select 48 fibers because that's a very common fiber count. If you have a certain diameter and you want to stick with that diameter, you can go with select OPGW by diameter, but of course that's going to prove to be much more restrictive in the designs that are going to be presented to you. So for today, we're going to start with the select OPGW by tension. So I'm going to pop up the screen and you can select your loading conditions, or you can click on the map to select your loading conditions. So we'll do that. So if I'm living in Texas, well, we got all 3 here in Texas, so I could select the area of Texas that we're in. And if you think you're close to a loading district boundary, you can just put in the city and state. Now, it says here, start by entering the name of a state, and it's true, that works that way. But you can also just start typing the city and it'll come up. Now, if you live in nowhere USA, maybe the city doesn't come up itself. Pick the closest major city. So we're located in Arlington, so I will pick Arlington. You need to have a list of spans handy. Remember that later, and from that you should know what your maximum span is. I've already set up a list of spans that we will see later, and I happen to know there's no span more than 650 feet, so we'll put that in. What it's saying is, based upon standard sag and tension criteria, the recommended maximum design tension value is 6,182 pounds. So you don't need more strength than that. And that's just your usable portion of the cable strength. Of course, the rated breaking strength will be significantly higher than that. So to that, you should add your fault current capacity. And the program does not necessarily do for you, but if you look at the hint above, you can see how that number should be calculated. So I was talking earlier about 80, so let's use that. Now what you see on this table is a grid with cables by their MRDT value, by fault current value. So you see we've got cables from fault current of 0 to up to 250, and we have MRDTs ranging from 4,000 pounds to over 34,000 pounds. Each dot represents a specific cable design that we've already done. So by the way, if you get the process and you don't like what you get, you can reach out to us, and of course we're happy to do a new cable design just for you. But of course the process would still have been useful because it would show you that nothing kind of in the standard catalog was optimal for your particular application. That's still useful information to know. The color dots give you information about the type of cable that it is. So a blue dot is a type C cable. If you don't remember what a type C cable is, you can look at the hover over the question mark and it'll explain it to you. So that's a plain stainless steel center tube type design. A C cable is a aluminum clad. One of our competitors calls it a centrocore. So it's a stainless steel tube in the center of the cable with aluminum. For clad the stainless steel tube, that particular competitor, they put their stainless steel tube in an aluminum pipe, but the net result is about the same. A black dot is a type S cable, which for us is a stranded stainless steel loose tube cable. I started off talking about Brugg cables, and that's the design that they were known for. And a green dot is a P-type cable. It's an aluminum pipe with plastic buffer tubes in the center. So back to the chart that you see here, the red means that the dots in the red zone don't meet your criteria. Either the fault current is too low, down here, or the strength is not high enough. Got one cable here on the borderline. Cables in the green area are optimal. The orange area are more than what you really need in one dimension or the other. Either the fault current is higher than you need, or the strength is significantly higher than what you need. So ideally, you would pick a cable here in the green and play with the parameters a little bit. I want to a little stronger for some reason. Maybe I want to adjust my fault current up or down a little bit, but you get a band here that within which you can work. So for today, you can pick whichever dot you want. And in fact, you can look at multiple dots. So you can say, well, I want to look at this one. Looking at this. Yeah, okay, well, let's see. Let's look at this one instead. Yeah, okay, kind of interesting. I think I'll go back to this one. And basically, you get an overview cable specification. So your map fiber count, you'll see that the fibers are organized in 2 tubes. That means 2 tubes of 24. Your basic mechanical and electrical specifications, basic stuff that you to know. And you can download that information to keep for later. And so here's the spec that particular cable as downloaded in a little more colorful format. There's more information here than the basic information that ACES screen. So once you've selected your cable, you're ready to keep moving. Now, if I had just done the cable selection only, I would have already been done. So everything that follows here is that complete system option. You've got additional information here. In this particular case, I've already used project data from helping a customer once before. I happen to know that it's 59 spans. Automatic arrangement of splice enclosures will just be based upon real lengths, and it will say, you know, you need a splice point here, here, and here. You can control all of that and also download a very simple Excel template, which I will show you in a minute, and fill it in. And like I say, I did that already. So let's look at that. Okay, so as I say, from a customer a couple years ago, 59 spans, and it's a very basic template. It's the header giving you instructions, basically your tower numbers. You know, by default, it's just going to be 1, 2, 3, 4 kind of thing, starting from 0, but you could put in whatever numbers you wanted. Now, here you enter a code of the fitting type. So D for a dead end, S for a single suspension, DS for a double suspension. And it doesn't matter whether you use uppercase or lowercase. Then you're looking at your attachment height, then the span length between towers. Pretty basic stuff. You've probably generated a list like this and copy paste. You should be good to go and able to upload your data. So this. So I had already downloaded the template. And I can and all of the span data. I could have entered all of that by hand, but if you're working with 10 spans, no big deal. If you're working with 59 spans, it's probably easier to do it in Excel and upload it the way I just did it. And there's lots of useful things that you can do now that help out. So the first is you begin with what type of dead end do you want? Right now we offer U-bolt and formed wire. We will be adding a bolted type dead end option real darn soon. For suspension, you've got three choices. You can use a bolted suspension, a AGS type suspension single layer, or an AGS type suspension dual layer. Now, the program will do some restrictions on this. If you choose an AP type cable, it's going to allow you to only pick the dual layer type AGS suspension. The single layer types are good for S type cables and they're good for the other types of cables, but for an aluminum pipe, it's better to stick with this more traditional dual layer AGS type design. So let's stick with bolted. So an example of a bolted clamp is a Pre-Line Products cushion clamp is what they call it. And let me take this opportunity to point out that PLP on this accessory portion worked with us to develop ACES, and we greatly appreciate their assistance. They gave us a lot of input, and including their product data. Grounding, you have a choice between an aluminum or a copper grounding strap. Some customers like aluminum, some customers prefer copper, whatever you choose to use. So the program has already calculated the total distance, and it's calculated the number of towers that have dead ends on it with splice points, and then the ones with splice points. And right now you'll see that that's 0, and we'll come back to that in a minute. Number of towers with suspension clamps, and the number of towers with double suspension clamps. So to keep going, here is that fitting type, that code that was put into the Excel worksheet. Now I can override that here. So I can decide, no, I don't really want to have a dead end here. I'll just do a double suspension. And then you'll see that it's removing the option to put a splice point there because there's not a dead end there anymore. Back to this in a minute. I can control the tower type, so I can make mass change from a wood pole to H-frame metal construction. The other choices being a monopole, like a steel monopole, spun concrete pole, lattice tower, or H-frame wood pole. That affects the sort of attachment hardware that's used with the other items, the suspensions, the dead ends, and whatnot. So if I metal for now, is point oriented in the vertical or the horizontal position, and I can change that. Likewise, excuse me, that was for the suspensions. I can also control how they are. So is it perpendicular to the line, or is it in line with the line? And I can change that individually, or I can change it in mass here at the top. On my grounding straps, whether I aluminum or copper, two terminal configuration. So there's a terminal on both ends of the grounding strap. I want one end to be free. And again, I can change that in mass, or I can go and change it for individual poles. do I need an adapter for lattice towers? We don't have towers here. Well, let's make one. So we'll say that this one is a lattice tower. With this checked, that will be included in the bill of material that you will receive at the end of the process. The cable service length at the end of the route. So basically, that's how much cable is being left for splicing and storage. So I change that value here, and then I can override at a particular tower if I want to. Here is how much extra cable is used in the real length calculation. And there is a hint here to tell you that you use the linear distance plus your cable length, the linear distance plus what you've allowed at the splice enclosures, and then an allowance. So the default value is 2%, but maybe you want more, maybe you want less. Basically a 0.5% allowance for stag with the extra allowance for the splice prep is good enough. Now, as I say, I could have gone in and just said, I want to pick the splice points. And if I use a reel like this, 72-inch, the maximum cable length is 22,425 feet. And of course, I would, well, yeah, certainly I want a splice enclosure at the first and last. And then it's going to come and do the points. So it's using it just on length. So you see it skipped this here and here and just kept going. Now you might say, well, no, I really do need a splice point here, so I'll go ahead and put one there. So when you've your tower information entered and you've picked your splice points, ready to move on. Of course, you can download all of this for future reference, and then of course it could be re-imported if you needed to adjust it later. And you get this pictorial representation at the bottom of what you've done. Right, so I added that lattice tower. Indicated where I have a double dead end without a splice in it. And when I'm finished, I'm ready for the next phase. And this is where you calculate your reel lengths. So I had already picked this wooden 72-inch reel, but I can do whatever I want here. If I pick automatic, what it's going to do is it's going to go ahead and pick the non-returnable wood reel, and it's combining lengths. Now, a lot of people don't like doing that. So you've got one cable here, cable links here, and then it's put some over here. I don't know about that. And I don't know why it, honestly, I don't know why it picked a metal reel here. So let's go back. What it's telling me here is that I need 3 links because of where I picked my splice points. And you can do kind of whatever you want. It's telling you the maximum length of this cable that will go on any particular reel. So if I want to, I could just, okay, well, I'm going to move all these links here. Okay, I don't like that. Let's see, what if I put this? Or the big question is, make a mistake. So I've got, oh, yeah, it's not letting me make that mistake. So I can't put a 13,993 foot length on a cable that can only hold 12,392. So it's telling me I have to put it on the larger reel. So it helps you not. So it's telling you've got these lengths on these reels, you get this total. And it's also giving you a gross weight, which is good for planning to make sure that you have the appropriate equipment to offload the cable when it arrives. And so, as I said, you can play around with this and have loads of fun. And then you can see the results. So it's reminding you here, the next step is the calculation of tension and sags, because remember, that was sort of the point here, is I want to optimize my cable design based upon really the cable really needs to do. So now this information here is, you probably, it's going to put it in the ballpark. It's going to confirm that that you've picked the best design for you. You probably still need to take the cable, run it through PLS CAD to get your final data. Plus PLS CAD get a control over the options that you're able to use, particular wind conditions. This is pretty basic, but it does put it in the, not just put it in the ballpark. It's going to be proved to be the right design. PLS CAD is just going to help you in the. So anyway, so you've got your segments here, and it's to what the sag is, what the tension is, how much sag you've got in there. The sag is a percentage of the span. You see here this sag after drawing. What that really means is it's the final sag after creep. And it's dividing sag between the horizontal component and your vertical component under the heavy loading conditions. Now, if you thought you picked the wrong one, you can go back, redo it. And again, you can, or you can just pick it here, whatever you want to do. If you want to change things, change things. So if I wanted to pull in the cable instead of 230 pounds, I wanted to pull it in at 300 pounds, it's going to adjust all of the information for you. So as I say, you can dial in design using this information. Got, you're happy with what you've done, you can download it, and then you could go on to, which is look at vibration damage. Right now, for OPGW, 98% of OPGW are less than 3/4 of an inch in diameter. So we consider that spiral vibration dampers are the way to go. There's a so-called standard spiral vibration damper, and then you've got high mass SVDs, which basically one high mass SVD equals 2 standard vibration dampers. And so, you don't have to buy as many of them, but the same. But it's time during install, you just put on one big high mass spiral vibration damper versus 2 standard ones. And then these results. And that leads to the last step, which is calculate the bill of material. So everything that you've done to this point, you click the Calculate Now button, and it's what's it's calling a specification, which is really just a bill of material, which you can then download. And what you get is bill of materials. So here was the cable design that you picked, how much cable that you need. If you click on the link, it'll take for some basic information about that particular cable type. Your splice enclosure, you here where you can get some information about what the program has picked for you. For all of the accessories, it's going to take you to PLP's website, where again you'll get this basic information about that product. And you can see that it's telling you you need 4 closures. In addition, you need this many of this particular splice tray, your heat shrink protection, your heat shrink splice protectors, cable storage rack, a Coyote Defender, and of course, you know, so, well, I don't really need bullet resistant, so I'll drop that. Yeah, I mean, once you're at this point, you're in control. Because of the tower type, it's telling you how much banding material that you need. So the band itself, as well as the buckle that go with it. Then you're down to your accessory, your dead end, the catalog number, again, a link. To that particular. And then all the rental items go with it based upon those tower information that you put in. You've got your suspension clamp, your double suspension, but also things like your ankle shackles, Y clevis eyes, yoke plates. All of that information is given here for you, your down lead clamps. And what we do here is down leads for OPGW, we assume, because this is kind of my thing. If it's a metal cable, I use a metal down lead clamp. If it's a plastic cable, meaning ADSS, I use a plastic down lead clamp. It doesn't mean you can't do something different if you prefer, but that is, you know, what I. And remember those grounding wires, so those are there, and your spiral vibration damper. So you've that information for you, and you're ready to send out your RFQ. And that is the GW complete system. And as I say, I'm going to move on now and just look at ADSS, just cable selection only, because everything after the cable selection process is pretty much the same for the 2 cable types. So ADSS selection only. It's, by the way, it's warranty. Information about the ADSS cables that we offer. And ADSS cable selection starts with this question: is rodent protection a concern for you? And the answers are, no, I'm not worried about it. A little bit of a concern. It may be more of a concern, or it's definitely a concern for me. And that is a direct bearing on the cable selections for us. And by the way, the reason that we do that is the UTC has just published a white paper, and of course I kind of had inside information about what it was going to say. they surveyed utilities around the United States about the problems that they were having with ADSS. Now, the study was broader than that, so I should really say one part of the study was to ask utilities around the country what problems they were having with ADSS. And it's probably no surprise to you listening that the number one problem was shotgun damage. But a really close number two problem was rodent damage, and particularly squirrels. So in CAB, we actually have various rodent resistant alternatives for ADSS. And so we thought we should, people are having substantial problems with rodents. And we are working on the shotgun resistance too, by the way. It's just, that's not yet part of this program. Future version, we probably will. Doing some testing on that. Anyway, the way that you get rodent resistant is basically twofold. One is that you can use fiberglass. Just plain fiberglass yarn gives a cable kind of a C level. You know, if you're on school grading system A, B, C, D, F, aramid basically gets an F. You know, rodents are quite happy to chew on cables with aramid in it. It doesn't deter them one little bit. So in that regard, aramid gets an F. In terms of strength and just anything other than rodent resistant, aramid gets a definite A, but rodent resistant, it's an F. Fiberglass gets you a C right off the bat. Now you can add a deterrent to the jacket and you can get that up to about a B. With the aramid, the deterrent you could add, and you could get that up, yeah, arguably to about a C. There is something that you can do there. For purposes of this program, though, if you indicate any level of rodent resistant, we immediately go into fiberglass. And then if rodents are a high problem, the best thing that you can do is a double jacket cable with FRP rod for strength instead of yarn. That gets you an A. And you can even add a deterrent and you can get that up to an A+. So this is an important question. That's why we started with it. And then there's also the voltage you'll see later. Tracking resistant can come into play as well. And so there's information, important information in the hint that's here. So we're going to be kind of more typical today. We're just going to stick with no danger of damage by rodents. Your voltage comes into play and how many jackets do you use? For distribution applications, single jacket cables are common and they're a perfectly fine solution for you. With a single jacket discussion, with a single jacket construction, you get a smaller diameter, you make the lighter, and you also make less expensive. So for distribution applications, that's fine. And here too is another example of we have a ADSS 101 webinar where I talk about that also in nauseating detail. And for today, let's just say that for distribution voltages, single jacket is fine. When you start getting above that, you think, yeah, I probably should use a double jacket because although the diameter goes up and the cost goes up, the reliability goes up with that construction. And so we think that's better. And then by the time you're at 230 kV, you are definitely in the realm of tracking resistant jacket. So this is kind of a rough way of categorizing the cable design type that you need, but it's pretty good. So for today, let's assume it's a distribution application, and let's go with 48 fiber. Now, ADSS, you also have fibers per tube is an important. So like here at 144, I could either do 6 tubes of 24 or 12 tubes of 12. And a lot of customers for the 12 fiber tubes, we do both. I do think that 24 fiber tubes, what the effect there is it gets the cable diameter down, which again goes back to reducing cost and weight. And I think 24 fiber tubes are great because it coordinates very well with the splice trays that are used in the marketplace today. But some people still prefer the 12 fibers per tube. So let's stick with 48 and let's stick with a pretty traditional 4x12 construction. And then again, we pick up with tension. What tension do you need? Do you know it? Well, most people don't. So let's just say no. And back to pick loading district. So, and by the way, you could do custom. So you could add a particular ice thickness that you want. So let's say for some reason I want to 0.4 inches of ice. If I want to, for my international customers, you can, instead of starting with English units, you can enter the metric ones and it'll convert it. So it goes either way. But let's go back to 0.4 again for whatever reason. And then wind pressure value, if you know it, I don't know, let's see, 4 pounds is the NESC. Let's just go with 5 pounds for some reason. And again, your max length. So let's 300. How much sag do you want? Now for the ACES world, what's most common is 1%. You also see 1.5%. And I've also learned that companies are out there saying less than 1%. I don't think that's particularly idea. I think that that's already kind of tight. Metal cables are generally more in the range of about 2%. So already you're kind of tight there with ADSS. You do kind of like the tightness in one sense because ADSS is very stretchy. And so by installing it tight, you do some mitigation of sag under wind and ice loading. But going below 1%, I think you've already got kind of a banjo string up there. I wouldn't do it, but some people are doing it. So today, let's stick with 1%. And then you get what your design options are back to the information that's up here. So it's telling you you can use an aramid double jacket, you can use a double jacket, or you can go with fiberglass if you want to, and it's explaining the pros and cons of each type. For a distribution application, the aramid single jacket is probably the most common, so let's just stick with that. The cable spec for you. Again, basic information about the cable. You can download those characteristics. And pull up the spec. Gives you more detail about the cable design. And at that point, because for ADSS, I just wanted to show how the cable design worked. Really, we're done. I mean, just for fun, let's go back and look at what it would do if I said, no, I got a real big problem with squirrels. 48 again, no, don't know that. Let's stick with standard heavy. Let's say I've got, I don't know, 400 feet. For this cable, I'm going to let it go 1.5%, and it's picked a design. Then you download the specs. And incidentally, see that it automatically names the, and it does so in a way that you can't accidentally overwrite what you might have done before if you're doing kind of what if analysis. an in-air defender, which is using the fiberglass reinforced plastic rods for strength, as well as armor construction. And again, all the specifications there. When you're doing the system, there are some more error checks in there that I didn't show in the interest of time. And now that we've gone through the complete system with OPGW, you could do it for ADSS. You've also seen how the cable selection works. Best thing to do is please go to our website, try it out with it. If you have feedback for us, please let us know. This is this is a product that we intend to continue to develop further and refine. So we very much welcome any comments that you may have. And at that, I'm going to open it up for the Q&A portion. So please, if you have questions, please let me know. It takes me a minute here to go over here to Q&A. Okay, so questions. Okay, people ask, variant process and corresponding spreadsheet and output, what does InCab get out of this? Well, we're in business to sell cable, so we're hoping if you've used our software, it's steering you towards an in-cab cable, so we're kind of slightly stacking the deck in our favor to get your cable order. What was that ADSS? Was there any mention of excess sag and ice loading? I don't recall. I'm not sure what you mean by excess sag, but I see my colleague Justin Fry has given the title of the UTC report. The title is ADSS Fiber Lifecycle Research Report, July 2020. I'm sure if you go to the UTC website, which would be utc.org, utc.org, you should be able to find a copy of that report. If you're a member, I think it's free. If you're not a member, they charge you. I don't remember how much. Do you have any option or to do or share tension charts for ADSS cable? We do is yes. Short answer. Customers are used to seeing ADSS tension data presented in charts, and we do those as well, but we kind of like what we do in this system. If you remember what you saw for the OPGW sag and tension portion of the complete system, we do exactly the same thing for the ADSS. So how access the software? Well, it's as simple as go to our website and click ACES, and then you're able to use it. So thank you. I'll say you're welcome, because it is our pleasure to give things like this. I enjoy doing it. Aha, good question. Up to what voltage is InCab providing track resistant jackets? It's a question of field strength, and the maximum field strength is 25 kV. That's actually not part of this at the moment. To get into field strength analysis, we sort of do that on the side. So by the time you're at that point, yeah, you need to contact us. But that's actually a really excellent question. Let's go back real quick and see what we've gotten at 30 kV or more. Everything so far is what you've already seen. And so you get a cable with the TR in it, which means a track resistant jacket. And so again, you download the specifications. My Q&A screen is locking the screen. And so you get a cable here. Outer jack is made of tracking resistant polyethylene. And by default, for us, it's a 230 kV track resistant cable. It's always going to be a double jacket construction, and that you didn't get the option there because that's what we would do. Otherwise, detailed information. Okay. Okay. Other questions? Oh wait, there are more questions. Typical field strengths at 500 kV, 345 kV, and 230 kV. In short, when do you start to exceed 25? Been in discussions about space potential. It is understood configuration has an impact on voltage. I mean, I gotta say that's kind of outside the scope of today's presentation. In ADS Engineering 101, I touched on that. Even then, I didn't go into this level of detail. I don't know the typical field strengths at those voltages. Because it depends completely upon the line geometry. That I guess for fun. By the way, thank you for your participation. If anybody wants to drop off at this point, you absolutely will not hurt my feelings. But since there is interest in this field strength topic, I will show you what we can do. If you want to hang around, great. If not, again, appreciate your attendance and look forward to seeing you at a future webinar. Please feel free to give us comments. You can write us at webinars@incabamerica.com. Better, is that right? Webinar or webinars? Just if you can respond in chat and let people know if it's webinars@incabamerica.com or if it's webinar@incabamerica.com, because I don't remember which. And for you that want to hang around for 5 minutes, I'll give you a primer on how you do field strength calculations. Gotta get this out of the way. Sorry, I gotta find a program for that. Here we go. And for everybody that said thank you, you're welcome. Again, pleasure. And I very much appreciate your participation. Okay. All right, so what you have here, and I need to make it bigger for my old poor eyes. Do for that is you would geometry of a line and you get something that looks like this, a real mess. The color code, basically any above green is bad, and because I not set this up correctly. But what you're seeing here is here's one of the phase conductors, here's a phase conductor, here's a phase conductor. And because this the spacing for this particular project, actually for like a 138 kV line, I think. Oh no, it says 500. The spacing is wrong. I know. I think I played with it at some point, and so the field strengths are terrible. But you basically have to do this process. This is just one way to do it. Yeah, 8 feet, and the offs are like 5 feet, so that's just not right. This is kind of, I don't know what I was doing here, but I've changed all of the data. But you get the idea. You in 2 dimensions, you plot out where each phase conductor is in space, the fact that you've put in the line voltage. In this case, is what's driving the field. I hope that's the question. But to my way of thinking, it's for determining the field when you're working with track resistant jackets. Okay. I think that we are done. My Q&A screen. That's okay. Q&A. Okay. It's not. It's. I can't get back to my Q&A screen. There it is. Yes. Okay. Somebody says let's talk offline about chart resistant. That's great. Again, thanks everybody. Appreciate your and have a great day.